Millions of end-of-life tires pile up because they last for decades, and disposal is costly and controversial. But inside this factory, those tires become raw material again, through cutting, separation, and precise sizing.
First, the tire is reduced to chips, then cleaned of steel and fiber, until only rubber remains.
That rubber can become crumb, powder, or compact pellets that feed other industries like a standard commodity.
One of the highest value uses is rubberized asphalt, where crumb rubber modifies road binder or the mix itself.
We follow the full path, from tire yard to finished rubber granules, and finally to a road surface.
No shortcuts, no slogans, just industrial reality, where quality depends on separation, temperature, and particle size.
This is how a durable waste turns into a measurable product, one machine stage at a time.
A tire is not just rubber. It is rubber reinforced with steel wire and textile fibers for strength and stability. Those reinforcements make tires safe on the road, but difficult to process when they become waste.
Recycling means separating three streams: rubber, steel, and fiber, without contaminating the final rubber product.
Contamination is expensive because it damages blades, clogs screens, and lowers the value of the output.
Consistency matters too, because different end uses demand different particle sizes and cleanliness levels.
This factory is built like a pipeline. Each stage makes the next stage safer, cleaner, and more predictable.
The goal is simple: turn bulky tires into uniform rubber particles while capturing steel and fiber as separate streams.
Now we start at the gate, where the first decision is sorting, inspection, and safe handling.
The journey has 9 main steps, but each one is basically reduction, separation, and grading.
First comes inspection and preparation, so dangerous objects do not enter the cutting line. Then shredders reduce the tire into chips, creating a manageable feedstock for downstream equipment. Magnets pull steel out early, protecting granulators and improving rubber purity.
Granulators and air systems then create crumb rubber and remove the remaining fiber to meet product specs.
Finally, the rubber is screened, packaged, sometimes pelletized, and shipped or blended into rubberized asphalt. Receiving begins with weighing, unloading, and sorting by tire type, because feed consistency improves process stability.
Workers look for hazards, trapped stones, large metal objects, and liquids that could create slip or fire risks. Moisture and mud are controlled because wet material can stick to screens and carry unwanted dirt into the product.
Basic housekeeping matters: clear floors, marked walkways, and barriers that keep people away from pinch points.
Before shredding, some lines cut tires into sections to reduce torque spikes and prevent jams at the intake.
Bead wire is dense steel. In some systems, it is removed early to reduce metal load in the main shredder.
Operators monitor feed rate because steady flow keeps cutting edges cooler and makes output chip size more uniform.
Dust control starts here too, with extraction hoods and sealed transfer points that reduce airborne rubber particles. With prep complete, the first major reduction stage begins: primary shredding into coarse chips. Primary shredders use slow, high-torque shafts that tear the tire, producing chips large enough for separation systems.
The output drops onto a conveyor, where guards and sensors keep the line stable and safe.
From this point on, every transfer is designed to keep material moving and prevent buildup at chutes and corners. Inside the shredder, rubber flexes and snaps as it is sheared, creating the first controlled product: tire chips.
Chip size is influenced by cutter spacing and screens, so operators tune the machine for the next separation step.
A steady feed prevents overheating and reduces sudden shock loads that can break teeth or stall the shafts. The chips travel on covered conveyors to limit debris ejection and keep dust inside controlled zones. At transfer points, rubber can bounce. Skirts and liners keep chips centered so they do not spill or contaminate floors.
Some lines use a secondary shredder to reduce chips further before granulation, improving throughput later.
Heat is managed with airflow and downtime because rubber dust can become a hazard if allowed to accumulate. Maintenance is constant. Sharp edges cut cleaner, waste less energy, and produce fewer long, stringy fragments.
After shredding, the stream still contains steel strands and bits of fiber, so separation equipment comes next.
The line is built so gravity helps, dropping material into chutes instead of forcing it uphill. Every chute angle is tuned to stop bridging, because stuck material becomes downtime and safety exposure. When chips exit the cutting area, they are staged briefly so magnets can capture steel without fighting dense piles. A clean chip stream reduces wear later, so the line often repeats magnetic capture at multiple points. Now the steel stream becomes visible. Twisted wire strands and bead fragments collected for metal recycling.
With most steel removed, the rubber stream is ready for granulation, where particle size becomes far more precise.
Magnetic separation is simple in principle, but critical in practice. It protects equipment and raises rubber purity. The magnet strength and belt speed are balanced, so steel lifts cleanly without pulling rubber along with it. Steel can appear as long strings. Cutters and combs strip the steel off the magnet belt into a controlled drop zone.
Operators check steel contamination in rubber by sampling downstream, looking for shiny fragments and wire strands. Some lines include a second magnetic stage after granulation, because smaller steel fragments appear during fine cutting.
Recovered steel is compacted and shipped as scrap, turning a waste component into a separate recyclable product.
With steel largely removed, the rubber stream becomes lighter and cleaner, and the line can move faster without damage. The next challenge is fiber, light textile strands that do not respond to magnets and must be separated by air.
From here, the goal shifts from removing metal to controlling particle size, because customers buy rubber by grade. Granulation begins now, turning irregular chips into consistent crumb that can be measured, packaged, and sold. Granulators cut rubber chips against fixed knives, producing smaller particles with more uniform shape and size. Water is sometimes used for cooling in certain systems, but many lines rely on airflow and controlled duty cycles. After cutting, crumb travels across vibrating screens that separate coarse pieces from finished product, and oversize return.
Oversized material is recirculated because uniformity is achieved by repeating the cut and screen loop. Fiber removal uses air separation. Lighter textile strands lift and drift, while heavier rubber falls cleanly.
The cyclone concentrates fiber into a collection bag, while the cleaned rubber stream continue to final screening. Even small fiber contamination can affect asphalt blending, so plants tune airflow to meet strict cleanliness targets.
At this stage, the product begins to look like a commodity. Black granules that pour consistently and behave predictably.
Different customers want different sizes, so the line can switch screens and knife settings to change grading.
Coarser crumb is common for some molded products, while finer crumb is preferred for asphalt modification and blends.
Clean rubber also means low steel content, so magnets are often placed again after granulation as a final safeguard.
When the stream is stable, the plant can run continuously, packaging product while keeping samples for quality tracking. Now we move to fine grinding, which turns crumb into smaller particles when a customer needs powder-like material.
Fine grinding can be done at room temperature, where rubber stays elastic and is cut progressively smaller.
Or it can be done cryogenically, where rubber is frozen, becomes brittle, and fracture into sharp-edged fine particles.
Both methods target the same goal:
tighter size control, and cleaner feeding for downstream industrial uses.
For asphalt, particle size and surface area influence how rubber interacts with hot binder during blending. Ambient grinding keeps rubber flexible, so cutting is more like slicing than shattering. Because rubber resists cutting, mills use multiple passes, reducing size step by step through screens.
Temperature rise is monitored because excess heat can smear rubber and reduce particle definition.
Airflow carries fines to collection, keeping the chamber clear and reducing dust escape at transfer points. Ambient particles often have a rougher surface, which can increase interaction with binders in certain formulations. Operators adjust screen size to hit a target distribution, producing a consistent product lot after lot.
Sampling is frequent. A handful of rubber is checked for fiber strands and metallic glints under bright light. When the spec calls for even finer and more uniform powder, cryogenic processing becomes attractive.
Cryogenic lines add complexity, but they can fracture rubber cleanly, reducing the energy spent fighting elasticity.
Safety is critical around cold gases, so ventilation and oxygen monitoring are part of the operating routine.
Once rubber is cold and brittle, impact mills break it into fine particles with sharp, consistent edges.
Next, we compare the cryogenic stage in detail, and then return to screening and final quality control.
Cryogenic grinding begins by chilling rubber with extremely cold gas until it loses elasticity.
Brittle rubber fractures cleanly, so mills can produce tight particle sizes with less smearing.
Cold processing can create more uniform particles, which helps when precise blending and feeding are required.
But the trade-off is infrastructure. Insulated lines, gas handling, and strict ventilation to keep conditions safe.
After grinding, the product warms back toward ambient temperature before packaging, preventing condensation in bags. Whether ambient or cryogenic, the next gate is the same: screening to confirm size distribution and remove oversize.
Quality control keeps lots consistent, because asphalt plants and compounders depend on predictable flow and behavior. Now we move into final grading and packaging, where the rubber becomes a product ready for shipping. Screening separates rubber by size, using vibrating decks that let smaller particles fall while larger pieces travel onward.
Even tiny differences in size can matter, so plants use multiple screen cuts to hit a narrow distribution window. Oversize is not wasted. It returns to grinding, keeping yield high while maintaining strict product consistency.
Fiber is checked visually and by airflow performance, because light strands can reappear if settings drift.
Metal contamination is checked with final magnets and manual inspection, because asphalt customers demand clean rubber.
Moisture matters too. Wet crumb clumps and feeds poorly, so storage areas stay dry and sealed from weather. A good product pours consistently, with minimal dust and no visible fibers, behaving like a standard bulk material. Samples are archived so the plant can trace any issue back to time, settings, and incoming tire stream variation.
Once graded, rubber is packaged into bags, boxes, or bulk sacks, depending on customer handling equipment.
Seals prevent moisture uptake and contain dust, which helps the material ship safely and feed reliable at its destination. Some customers ask for densified pellets to improve flow and reduce airborne dust during feeding.
Pelletizing changes handling more than chemistry, turning crumb into a more uniform, free-flowing feedstock.
Now we follow those products into a major end use: rubberized asphalt, built-in plants that run hot and fast.
The same recycled rubber that starts as a tire can end up modifying road surfaces that carry heavy traffic every day.
Pelletizing begins by densifying crumb under heat and pressure, then cooling pellets so they keep their shape. Pellets reduce dust and improve flow, which helps automated feeders deliver consistent mass over time.
Bulk sacks are weighed and strapped because shipping needs stable loads that will not shift in trucks or containers.
Warehouses stay dry to prevent clumping, and floors stay clean to avoid cross-contamination between product grades.
At shipping, samples travel with each lot, so downstream users can confirm quality before blending into their process.
Now we step into asphalt production, where rubber becomes a performance modifier under high temperature and mixing energy.
Rubberized asphalt can be made by two pathways: wet process, where rubber modifies binder first, and dry process, added in mix.
Both aim to improve road behavior, but they differ in equipment, timing, and how rubber interacts with hot binder.
Before we blend, we need clean, graded crumb rubber, because impurities can disrupt pumps, valves, and mix uniformity.
With product ready, the story shifts from recycling to infrastructure, where material science meets logistics and scale. Rubberized asphalt uses crumb rubber from tires to change how the binder and mix behave under heat and stress.
When rubber meets hot binder, it can swell and interact, increasing viscosity and changing elasticity of the binder.
Particle size influences reaction speed, because smaller particles have more surface area exposed to binder.
Plants choose a method based on performance targets, available equipment, and local specifications for paving. We start with the wet process, where rubber modified binder is produced as a separate step before mixing.
Then we compare the dry process, where rubber is dosed into the mixer like an engineered aggregate component.
In the wet process, crumb rubber is blended into liquid asphalt binder in a heated tank with strong agitation.
Temperature is kept high so binder flows and rubber can interact, while operators avoid overheating and fume spikes.
Rubber is fed steadily to prevent clumping, and recirculation pumps keep the blend uniform throughout the tank.
A holding period allows interaction time, while mixers keep particles suspended instead of settling to the bottom.
Technicians check viscosity with small samples, watching how the binder pours and coats a metal paddle.
If rubber is too coarse or too dirty, filters and pumps suffer, so clean graded crumb is essential upstream. Once ready, rubber modified binder is transferred to the mix plant, where it meets aggregate and becomes hot mix asphalt. At the mixer, hot aggregate combines with modified binder, producing a dark, uniform mix that must stay within temperature range.
The mix is loaded into trucks quickly because cooling changes workability and can affect compaction on the road.
On the paving site, the paver lays the mat, and rollers compact while the material is still hot and workable.
Wet process rubberized asphalt is often used for performance, but it demands extra blending equipment and process control. Next, we compare the dry process, where rubber enters later and behaves differently inside the asphalt mix. In the dry process, crumb rubber is added during mixing, alongside aggregate, rather than pre-blended into binder.
The rubber acts like an engineered additive, and mixing time is managed so the rubber distributes evenly through the hot mix.
Feeders must be accurate, because too little rubber changes nothing, and too much can affect stability and compaction.
Particle size and cleanliness still matter, because fiber can clump, and metal can damage the mixer and conveyors. Dry process can simplify binder blending, but it shifts control into the mixer, where uniform distribution becomes the key challenge.
On the road, crews watch temperature and compaction closely because rubber changes workability and cooling behavior.
Both pathways depend on the same upstream discipline: stable crumb production, clean separation, and consistent grading. With asphalt covered, we return to the recycling plant to see what can go wrong and how operators prevent it.
The biggest enemies are dust, heat, and contamination, because they reduce safety, damage equipment, and lower product value.
Blade wear changes particle shape, so maintenance schedules are tied to product quality, not just machine uptime.
Air separation settings drift with humidity and feed composition, so operators tune airflow and recheck fiber removal often. When control is tight, the plant runs like a system. predictable streams, stable throughput, and consistent rubber product lots.
A tire's durability becomes an advantage again when it is processed into clean rubber, separated steel, and captured fiber. Those outputs feed real industries, from molded rubber products to asphalt plants building roads under heavy daily demand.
What looks like waste becomes measurable inventory, but only through precision, cutting, separation, grading, and strict control. From a pile of tires to a finished road surface, the story is industrial discipline, turning a hard problem into usable material.